Hello, my name is Gerardo Zavala and I'm going to present the progress of my project Mechanical Components Classification from 3D Objects for the Smart Manufacturing course. Okay, so I'm going to give a very brief introduction about what is computer vision. I'm pretty sure a lot of you already know this, but computer vision is a subfield of artificial intelligence. We all know that every day tons of images, videos, and text are uploaded into social networks, and it is quickly becoming a very important field. And what is computer vision? It is the capability to develop techniques to help computers understand videos or images. So what does it mean? So there are different applications of computer vision. There is object classification, which the main goal is to categorize the object in the photograph or the video, object identification or detection. For example, you want to identify if there is a person in the image, or where is the person in that image, or how many people is in that image. And there is another one which is object verification. Is there an object in the image? And all these type of methodologies or problems can be used for different applications. For example, self-driving cars, identify damage crop, quality assurance, operational efficiency, and machine vision. So how is computer vision done? There are two main open libraries to develop deep learning models. It is PyTorch and Keras. These libraries facilitates the use to develop neural network models, and the main process or the full process of a computer vision project is to load the images, process the images, and the main goal is to create a new set of images, trying to have a simplification and a normalization of the images with the goal to achieve better results in the model. So talking about the specific of this project, I am using the MCV dataset to training and testing, which is a dataset that contains pretty much about 58,000 mechanical components, and it is divided into 68 different classes. And the main goal is to evaluate these 3D objects of different mechanical components and being able to classify them. You can see in the right side of the slide the image where it shows the class and the quantity of images it has. It has a lot of variations, since we have classes with a lot of images to train and other ones with a small sample to train. So what I did due to computational constraints is a data reduction. So I take the top 8 classes and that's what the ones that will be used to train and testing. So the total objects to train, it's a dataset which contains 24,000 points and 6,000 points to train. So what are the objects contained, or the data or the information contained in this dataset? It contains OBJ files, which are files that are used for 3D printing and 3D graphic applications. It has information about the surface geometry, the color, the texture. It doesn't have information about the light or the position. These type of objects are generated by a CAD software, and it's the end product or the final product of the 3D modeling process. This file format was created by Wavefront Technologies, and the advantage is that it can approximate surface geometry without increasing the file size. How to read these type of files into Python? So I used a try-mesh library. You can see in the image that I'm using try-mesh load and the directory and the object that I want to plot or to show. And you can do any kind of rotation or zoom in and zoom out in Python with this library. Okay, so after I understand what type of data it has, I obtain a point cloud, which a point cloud is a representation of the geometric structure of that 3D model. It is a simple representation, it is easier to process, and we can sample always the fixed points, fixed number of points. For example, I can sample 1,000 points for each of the classes, or 5,000. In this example, I'm using 2,048 samples, and I'm plotting it with Matplot. And you can see how it tries to represent the previous 3D model that I showed you. Okay, so for this project, I'm going to use transfer learning. Transfer learning is just a method where you use a model that has been previously trained and validated for a specific task. This model can be used as a baseline model since it has already performed with acceptable accuracy. And these techniques are used commonly in deep learning and computer vision and natural language processing. It is a very good starting point for a baseline model. And in some of the cases, you will obtain better accuracies than with a custom model. Okay, so the architecture that I'm going to use is called PointNet. Okay, this architecture was developed by Charles R. Key and other contributors. So this architecture uses point clouds instead of voxel grids because they realized that in the previous researches, voxel grids are inefficient representations because the data it was very voluminous and it causes a lot of issues when doing the training. But the problem now is that with point clouds, there are three main constraints that appear. So point clouds are unordered. When you do this sampling, these points are unordered. So the algorithm needs to be invariant to different combinations of the points or permutations in the input set. Also, for example, if we rotate a chair, it is still a chair. You are just looking at it from another point, or you are looking for an upside view or a left side view, but it is still a chair. And finally, the network needs to be able to capture the interactions among all these points. So you can see in here that the architecture. So in the first part, it is using a symmetric function, a max pooling function, and the idea is to deal with the unordered points. And the network tries to learn optimization functions and criteria so it can select interesting or informative points of the point cloud representation. And finally, at the end, there is a fully connected layers that they aggregate all the previous learned optimal values into a global descriptor to being able to classify or to segmentate the data. So you can see these two very informative images. In the upper one, you can see it's the PointNet visualization. So it shows how the network learns a collection of point functions. So each of these cubes is a collection of point functions, and it selects representative points from each input point. It is showing 15 point functions. Okay, and in the lower image, it shows the visualization of critical points and the upper and lower bounds. So in the first row, you are looking at the original shape of the point clouds. In the second row, it shows critical points. So the algorithm is able to detect critical points that it picks as some kind of features that it will use. And in the third row, it shows some upper bound shapes and lower bound shapes. And if it is between those upper and lower bounds, the classification result will be that it will be a gun or any object that it's in there. So there was a need to do some processing for the data before entering into PointNet. So the points from the cloud are not uniformly distributed across the surface or the 3D model. So that would make some difficulties to the PointNet to classify them. So it was used a uniform sampling from those points. Also, since we have dense layers in the network architecture, we will need to fix the number of sample points from each mesh. I will select in the final results different number of sample points to see the differences in the accuracy. Also, the data needs to be shuffled. And I created batches of size 32, and I adjust the output layer since I'm already taking the same architecture. One of the most important parameters when you use transfer learning is to adjust the output layer for the desired number of classes, which in this case I am using 8. So you can see in the left image, I am still in the process of running the model since it takes a lot of time. It has a lot of parameters to train. So here it shows how it's using the architecture, and in the right image you can see that the output layer, it has dense 8, which is for the 8 classes selected. It has a total of 7,048 total parameters, and the trainable parameters are 7,042. So after this, you can compile the model, and I am using a sparse categorical cross entropy since we are in a classification task, and you feed the model with this command right here with 20 epochs. And finally, after it finished the process to train, I will evaluate the accuracy of the problem, or of the model, sorry. So the next step is to finish the point net, being able to finish the model runs for the point net. And also I want to try a different architecture, a custom made one, to see if I could achieve better results, or the point net it's a better architecture and I will obtain better prediction accuracy. So that are the next steps, and thanks all for watching.